Hello, James Flaten here with the Minnesota Space Grant with a very quick refresher discussion about doing math in science class and engineering class, in particular doing math with both numbers and variables and constants and physical values, where often a value has both a number and also associated units. So this is going to be a review, but this is the kind of math one might encounter, for instance, in a rocketry class. And so let's get started. I don't expect my students in my freshman rocketry classes, for instance, have necessarily taken physics. I do expect that my students know how to do math. So just a few pointers here. Um, of course, let's start with numbers. So numbers like 2 or 7 or 3/5, okay? And then operators, operations that you might do on these numbers. And eventually you'll do operations on variables and constants and values as well. So operations could be, for instance, addition or subtraction, or, well, there's an operation right there. That would be a division operation, or multiplication. Multiplication, sometimes you first learn that as an X. I will rarely use that. I might use a star to indicate multiplication. I might use a dot to indicate multiplication. And then there are powers, okay? And so I might use a caret to indicate a power, or else a superscript to indicate a power, like 7 cubed, okay? Now, when you're doing operations, of course, you have to bear in mind the order of operations. So typically operations occur with divisions and multiplications and powers first, left to right, and additions and subtractions later, also left to right. And you can use parentheses to make sure that you're getting your point across. So if, for instance, I say 2 divided by 3 squared, that might almost be ambiguous. Is it 2 divided by 3 squared, or is it 2/3 squared? And if I put parentheses around the 2 divided by 3, then it's very clear that I mean 2/3, and then I'm going to square that quantity. Or if I did 2 divided by 3 squared and put parentheses around there, it's very clear that I want 2/9, 2/3 squared. So use parentheses. It's a good idea, just to make sure it's very clear. And if you're coding an Excel spreadsheet or something like that, using parentheses can make sure that you and the machine agree on the order of operations. Another thing to pay close attention to is what's in the numerator and what's in the denominator. So for instance, if I have 2/3 divided by 7/5, well, essentially the numerator of a numerator is definitely in the numerator, and the numerator of a denominator is definitely in the denominator. But the denominator of a numerator is actually in the denominator of the whole expression. And the denominator of a denominator is actually in the numerator of the whole expression. So there's the 2/3, and there's the 7/5. And notice the 7 stays in the bottom and the 5 ends up on top. And then I could say 2 times 5 would be 10. 7 times 3 would be 21. Now, when you're working with numbers, you are perhaps encouraged to, sometimes too quickly, to put it into a calculator and get a decimal value. And that's fine, but it turns out that sometimes you lose something if you do that too quickly. In fact, you may lose sort of the broad view. And so my recommendation is when you're working with expressions, numbers first and then eventually variables, try to reorganize them, try to simplify them, try to see if anything cancels out before you do what I would call an execute. An execute means put it into a calculator and try to get a final value, possibly in a decimal form. Okay, so for instance, if I happen to have the following situation, I have 12 plus 3 minus 12 plus 7 equals, well, you might say 12 plus 3, there's 15, and take away 12, but you might also notice, wait a minute, there's a plus 12 and a minus 12. Let me just make those go away, and then the answer is going to be only what remains. The 3 plus 7 is 10. So there's an example of cancellation, or just kind of paying close attention and noticing what's really important and what actually disappears. That's a situation where you have pluses and minuses, where you get some cancellation. Of course, there's also the possibility that you have numerators and denominators. So if I have 3 times 12 over 12 times 2, well, you might notice there's a 12 in the top and a 12 in the bottom, and there's multiplication in both cases. And so I can cancel that, and this will leave me with 3 over 2. On the other hand, does not work to say 3 times 12 over 12 plus 2. That would not work. Now I can't cancel the 12s. Okay. So simplify. And simplify involves often cancellation. Watch for cancellation. Watch for things that disappear and hence don't actually matter in the final result. Okay, so there's a few comments about numbers. Let's talk a little bit about variables. So variables typically are letters. They might be Greek letters, they might be English letters. But the letters usually mean something. So for instance, T might possibly stand for time, or W might stand for weight, or A might stand for acceleration. You just have to be a little careful though, because later we're going to also use letters to be units. So I might have 3 seconds. And if I decide to use S for seconds, I probably shouldn't also in the same calculation use S to mean speed, the variable speed or the unit seconds. So choose what letters are going to mean what, and sometimes a letter will refer to a variable, and sometimes a letter might refer to the unit that goes on some sort of a value. Okay, the nice thing about variables is that you can do math on variables just the same way you can do math on numbers. So if, for instance, I have 3t plus 7t, well, t, and then a whole bunch more t's, and eventually I'm going to come up with 10t. Or if I have 3t squared divided by 4t, well, I notice a t times t up here and a t here, and so one of those t's would cancel with one of those t's, and I would end up with 3/4 is the number, and t is the remaining variable. So there's an example of simplification, cancellation, in this particular case by noticing the variable appears in the top and in the bottom, and I can cancel it. Ultimately, if a given variable drops out, so for instance, if I have 7, let's say I have a variable L and another variable Z, and then later on I want to divide, for instance, in the middle of some sort of a calculation by 5Z. Well, I notice there's a Z in the top and a Z in the bottom, so I can cancel it. I like to do that explicitly. I like to write down the variable and then strike it through, possibly with strikes to the left or strikes to the right or triple strikes or double strikes, so I can be clear on what exactly canceled with what. And I end up here with 7/5 L. Now notice it looked like Z was going to be important because Z showed up in the numerator and Z showed up in the denominator, but it showed up in the same way. And so ultimately the final answer doesn't depend on Z at all. So this is a situation where you think something is important perhaps, and you realize by doing the calculation that I don't even need to know Z because the answer will be independent of the value of Z. And so if you have Z, you don't need to use it. And if you don't have Z, you don't get stuck because you weren't planning to use it anyway. You'll only notice that though, if you write out your equations this way and explicitly show that Z has canceled out. With variables, sometimes, often, in fact, that's the depth I'm going to go in this particular refresher. Let's say you have an equation and you know some things in the equation and some things you don't know, perhaps just one thing. For one equation, you can perhaps solve for one of the unknowns. If you had 7 equations, you could potentially solve for 7 different unknowns. That's beyond what I'm going to talk about in this particular quick refresher. But if, for instance, I say f equals ma, where in this context, F is a force and m is a mass and a is an acceleration. If I knew m and I knew a and I multiplied them together, I could solve for F. I could come up with F even if I didn't know it. Or if I take this relationship and if I divide both sides, let's say I divide both sides by, I'm going to write it again, and divide both sides by a. So on this side I have F over a, on this side I have m times a over a, so the a cancels, leaving only the m. And so now I have a new expression, m equals, I'll just write it over here again, F over a. Or I could start with the original expression, F equals ma, and I could divide both sides, not by a, but by m. And then I notice the m cancels. So in this particular situation, if I happen to know m and a and I need F, this would be the most useful equation to use. On the other hand, if I'm trying to figure out m, this might be a more useful equation. I've solved for m in terms of other things, and if I know those other things, I can find m. Or, this is the most common, in fact, you know the forces, you know the masses, and you're trying to figure out what's going to happen. So in that particular case, you don't know, but you're interested in the acceleration. This would be the most useful version of this equation. The equation comes in three variants, and depending on what you know and what you're trying to figure out, you might choose to use one of them. So in general, if there's something you don't know, solve for that. Get that thing by itself in front of the equal sign, and then everything else on the other side perhaps doesn't involve that variable, but involves things you know, and then you can calculate what it is that you are looking for. Okay, so very quick comments about variables. Constants are easy. So a constant actually looks a lot like a variable, except it's just something that I don't allow to change. So for instance, very typically pi is used. Pi is just a Greek letter, but pi is used as a ratio of the circumference of a circle to its diameter, and it turns out to be 3.14159, dot, 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 it keeps going beyond that. And so, generally speaking, whenever you see pi, don't assume that's something to solve for. Assume that just represents a number, and that's this particular number. Here's another constant. It's called g. And so g could be 9.8 meters per second squared, or g might be written as 32.2 feet per second squared. This particular constant refers to the gravitational free fall near the surface of the Earth. So this constant is used a lot in physics, at least. This is how quickly things pick up speed if you drop them near the surface of the Earth, or how quickly they change their speed because of gravity, if nothing else is acting on them, including no air resistance. And notice in this particular case, the constant has a number and it has units. And the units are letters, and so these particular letters are not variables. These letters refer to specific measurements. So m is for meters and s is for seconds. And so this would be an example of this constant in a metric system with meters, and here would be the same constant in a imperial system, or sometimes called a US customary system, okay, where we use feet for length instead of meters for length. Both of these systems use seconds for time. So not much more to say about constants other than they don't change. And then, of course, there are the physical values. So G is an example of a physical value. A physical value typically has a numbers part and a units part. So 3 hours, that would be a physical value. That's a time, okay? 3 milliseconds, that's also a time, shorter time. 3 small time units as opposed to 3 larger time units. Or I could have 3 miles, or I could have 3 millimeters. So you'll notice that in this case, often the units, sometimes this might be written as 3 sec, or maybe even 3 ms. So you just have to be careful. Units are often multiple letters, and sometimes a given unit, milliseconds, which is 1/1000th of seconds, might be written as m-sec or ms, and so just beware that there are different ways to write the same unit. On the other hand, when you're doing calculations, units act just like variables. So for instance, if I have 3 seconds divided by 17 seconds, the seconds cancel, and I end up with a pure number, 3/17. And it doesn't really matter if S was for seconds or S was for something else, it's going to disappear as long as it's used in the same way, in this case, in the top and bottom. So that's a nice thing. Keep the units in the calculations, make sure they go along with the values that they're trying to represent in a single physical value. And then handle the units. And if you don't like the units, you can actually convert them. So for instance, if I have units of time, notice here are units of time, hours, here are units of time, milliseconds, and I could potentially take 3 hours and turn it into some rather large number of milliseconds if I want. So let me show you the way I like to do that. So I'm going to call this converting units. Okay. And so the key to converting units is you have to know the equivalency. So for instance, I know that there are 60 seconds in 1 minute. So apparently 60 seconds is the same thing as 1 minute. And I know that there are 60 minutes in 1 hour. And what that means is that if 60 seconds is really the same thing as 1 minute, then 60 seconds over 1 minute is a ratio who's equal to 1. And the reason it's equal to 1 is that the numerator and the denominator are the same thing. They have different units. They look different, but they are the same thing. Similarly, 1 minute over 60 seconds is also equal to 1 because the numerator and the denominator mean the same thing. What this allows me to do is it allows me to take some number or some value that I have in hours or minutes or seconds and convert it to something else, as long as it's the same kind of unit, like in this case, time. So let's say I have 3.5 hours, and I would like that to become minutes. Well, all I need to do is multiply it by something that has hours in the bottom to make sure the hours will cancel. And if I'm aiming for minutes, it would be handy if I had minutes in the top, so the minutes persist. And so how many minutes are there in an hour? There are 60 minutes in 1 hour. So the hour cancels, and I get 3.5 times 60. That's the number, and the units are minutes. So this is what, 210 minutes. So 3.5 hours is 210 minutes. And I could do this multiple times. For instance, let's say that I have 3.5 hours, and I want that in seconds. Well, I can get rid of the hours by changing them to minutes, and then I can get rid of the minutes by changing them to seconds. And now I just have to put in the numbers here to make this equal to 1, so 60 minutes in 1 hour and 60 seconds in 1 minute, and therefore the hours cancel, the minutes cancel, and I'm left with 3.5 times 60 seconds divided by 1 times 1. I don't always even bother writing 1 times 1, but more or less, this is collecting all the numbers together and collecting all the units together, but it turns out that most of the units in this case disappeared. So this particular procedure for converting units allows you to go from miles per hour to meters per second, because miles per hour is length over time and meters per second is length over time. Or, kilograms per cubic meter into grams per liter. In other words, some mass divided by some volume. Okay, we'll see actually a bunch of that in a minute. One thing you do have to be a little bit careful about is if you happen to have a unit that is repeating. So for instance, area. So let's say an area is 3 feet by 4 feet. So in this particular case, it is a multiplication. You even wrote it as an x, although often I will reserve x to be an x variable. But anyway, so the number here would be 3 times 4 is 12. And the units here would be feet times feet, which would be feet squared. That's fine. So I have area is 12 feet squared. Now here's a question. How much area is that in, let's say, yards squared? Well, A is equal to 12 feet squared, which is really feet times feet. And there are, to make those feet go away, I could say that there are 3 feet in 1 yard, but that only makes one of the feet go away. So I have to do that twice. 3 feet in 1 yard. And so now this feet squared, feet, goes away with feet and feet, and then I end up with yards squared. And so the answer is equal to 12 times 1, divided by 3, also divided by 3. So 12 over 3, and then the units would be yards squared. So if you happen to have a power of a unit, make sure that you convert each of the powers, not just one, but as many as there are. So, of course, 12 feet squared becomes 12 over 9, or just over 1 yard squared, 1 1/3 yard squared. Fine. Let me make one more plug for watching units carefully. So, for instance, you might encounter in a physics class, for instance, something like x equals 1/2 gt squared. So this is an equation that talks about how far you fall in time t if you are picking up speed at a rate of g. So in other words, if you are falling because of the Earth's gravitational acceleration. So this is dropping an object and letting it fall, and how far does it fall in the first second, and the second, third second, etc. Okay? And so let's say that I want to have something fall for 2 seconds. Okay? So x is equal to 1/2. G would be, let's do this in metric, 9.8 meters per second squared. So that's G. I'll put parentheses around it. And then I said I want to let the thing fall for 2 seconds. So there's 2 seconds. And then I need to square it. Okay. So the unit here is 1/2 times 9.8 times 2 times 2. That's fine. So that's the number. And then the number is 1/2 times 9.8 times 2 times 2. And the units are meters over seconds squared. That came from here. And then times seconds, but it's squared. This is handy because second squared in the denominator cancels with second squared in the numerator. And the ultimate answer is some number of meters. Let me just pull out a calculator and just see how many meters that is. Okay, so here I got my calculator and I say 1/2, that's 0.5, times 9.8 times 2 times 2, 19.6 meters. So in 2 seconds, I would fall if I started from rest, 19.6 meters. And I could change that into feet if I wanted to, or into any other length unit, as long as I know the conversion factor. I know the relationship between the new units that I'm interested in meters. If somebody was doing a calculation and at some point came up with the following equation, x is equal to 1/2 gt, and they forgot the t was squared, okay? Here's what would happen. This is wrong, but this is going to show you the benefit of keeping track of your units, okay? And so let's say you want to find out what happens in 2 seconds. So you go 1/2 9.8 meters per second squared times 2 seconds. So there's G and there's T, and it's not squared by mistake. And so I do my calculation and I get the following 9.8 times 2. That's the number. And then here are the units, meters per second squared times seconds. And I can get a value. So 0.5 times 9.8 times 2. Wow, look at that. There's a 2 in the top and 2 in the bottom. I didn't even notice that, but I should have. The 2's cancel, and I end up with the number is 9.8. But if I look at the units, I see this second cancels with the double here, and I get 9.8 meters per second. And now I should worry. And the reason I should worry is, wait a minute, I was trying to get a distance, and I came up with a speed. I wouldn't have noticed that perhaps had I not paid attention to the units and only came up with a number. 9.8, sounds good. Incorrect. 9.8 meters per second doesn't have the right kind of units. I was looking for a length and I came up with a length over time. You can't notice that if you don't keep track of your units. And the way to keep track of your units is to write them down and see if they cancel. And in this case, they didn't cancel properly. Keeping the units will never tell you something is right, but if the units are wrong, it is wrong. They will absolutely tell you if something is wrong, and that's worth it. Okay, so show your units, keep track of your units, and as long as the units work out, you have a chance. If the units don't work out, you are incorrect, and you have to go back and figure out what went wrong. And the answer, what went wrong, is this equation was messed up. Okay. Let's talk a little bit about metric versus what I'm just going to call US customary. It turns out that lots of people around the world believe firmly in metric system. That's fine. It turns out that this country, for historical reasons and perhaps for stubbornness, continues to use US customary units. And that's actually fine also. But if you work in this country, you need to know both. You need to be very adept with metric system, and you need to be very adept with US customary system. Some calculations, it's easier to do in one system or the other. And if you know how to convert units, you can do a calculation in metric and then convert to US customary or the other way around. In the case of rocketry, in the case of aerospace, a lot of the rules are written in US customary units. And so ultimately you need to know, is that faster than 25 feet per second or not? Now, you might want to calculate it in feet per second right off the bat, or you might calculate it in metric, especially if you have more familiarity with metric system, or if the values are easier to use in the metric system. But if you do that, you just have to change it to feet per second at the end so that you can answer the question, is that faster than 25 feet per second or not? So in the metric system, as we already mentioned, time is measured in seconds or hours or minutes, okay? And in the US customary system, time is the same, seconds, hours, minutes. So this is good. Both systems use the same units for time. On the other hand, the metric system uses meters for length and millimeters, centimeters, kilometers, multiples of meters, powers of meters, okay? And the US customary system tends to use feet or yards or miles, okay? Or inches. So the ratio between these things is different. This is a 12-to-1 ratio, this is a 3-to-1 ratio, et cetera. So these ratios are harder to remember. And these ratios are all powers of 10, which is handy, okay? On the other hand, if you have a calculator, it's no more difficult or easy to calculate things in US customary units than in the metric system. The metric system was particularly useful when you had to do calculations in your head, but that's actually not the case anymore. The metric system actually favors mass, and it measures mass in grams or often kilograms, whereas the US customary system favors force. And force in pounds is written as lb, okay? So there is a force unit in the metric system. It's called newtons. So a newton equals 1 kilogram times 1 meter per second squared. So in other words, the force unit is calculated using things that are here, meters and seconds. On the other hand, the US customary system also has a unit of mass, and it's called a slug, and nobody ever uses it, okay? It turns out the US customary system actually has 2 units of mass, and the kilogram is so much easier than either of them. One is called pound mass, and one is called slug. And my recommendation is avoid both if you can. So if your calculations involve mass, probably a metric calculation would make a lot more sense. Gravitational weight is a force. And I might use W to indicate gravitational weight. And gravitational weight is calculated as m for mass times g, that free fall acceleration constant. Okay. And so it turns out that if you know your mass, like in kilograms, and multiply by g, you will get a weight, and the weight will be in newtons. That would be how you do this kind of a relationship in the metric system. On the other hand, if you know your weight in pounds, because that's the force value for US customary units, and then there is g, 32 feet per second squared, then you can get your mass. And your mass will come out in the mass version from the US customary units, which is called pound mass. And so essentially it's the mass of an object whose weight is 1 pound. But pound mass and pounds are force. So pound force and pound mass are related to each other by a factor of g. Bluntly, it's complicated. It's unnecessarily complicated. The metric system really does do better by favoring kilograms, favoring mass, especially since Newton's laws tell you that mass is related to acceleration. And so mass is very often a very exposed thing in calculations. So finally, I want to do some calculations. First of all, some advice. Okay, so if you're doing math with variables, actually, I want to say if you're doing math with values, so values are things that have numbers and units, and if you don't know what they are, you might call them variables to be determined. I guess perhaps the first thing to do is find a relationship, an equation, relating what you're interested in, which is sometimes called the unknown. And if you don't know it, you often call it an unknown variable, with things you know. So, for instance, in my class, we talk about parachutes and things are falling, and there's force relationships when things are falling under parachute. And so a parachute equation might relate how fast you're falling with the mass of the object and the area of the parachute and a few other things. So if I'm trying to figure out how hard I hit the ground, how fast I hit the ground, the equation would be what is the terminal velocity, what is the speed I hit the ground with, as it relates to other things, including the weight of the object that's falling, or the mass of the object that's falling, or the size of the parachute, etc. So find an equation. Second, this is very simplistic math in this particular case. Solve for the unknown in terms of the things you know. So in other words, if I have a parachute problem and VT, terminal velocity, is the thing that I want to know, I just have to get VT by itself on one side of the equation and see what remains on the other side that doesn't involve VT. And so once I have solved for the equation, in higher math or more advanced situations, you might have multiple unknowns and multiple equations, but I'll just stay with one for this particular lecture. Once you have solved for the unknown, then all you have to do is put things into the other side and then simplify, okay? And watch, because you almost always know what is the type of variable unit you will have. So this is a time unit, or this is a speed unit, or this is an acceleration unit. And so as you are simplifying the other side, make the units go away until you are left, you've distilled it down just to the kinds of units you were expecting, okay? So step 3, I guess, is put in values which have numbers and units, both. Don't forget the units, please. Okay. And then simplify. Simplify. Okay. And sometimes you'll find that there are units that aren't going away. And the reason is you have hours in the numerator and you have minutes in the denominator. Well, you might want to convert the hours into minutes, and then the minutes would cancel out, okay? So I'm going to say when you simplify, this might involve unit conversions. And as the term suggests, simplified does mean it probably will involve cancellations. So in particular, I'm looking for things to cancel, but I might not be able to cancel them until I've converted them. Okay. Once things are as simple as you can get them to be, then I'm just going to say execute. So execute more or less means just take the numbers and put them in a calculator and get the final answer as a single number, perhaps a decimal number. And then here's the last step that happens fairly often, at least in aerospace calculations. Convert to what I'm going to call needed units. And what the reason there might be needed units is because you might be saying, is that bigger than or less than 25 feet per second? In other words, there's a threshold, and threshold is a value with units, and I need to be able to compare to that value with units. And so you can either take the threshold and put it into the units you found, or you can take the answer you found and put it into the threshold units. That's usually preferred. So convert to needed units, especially if a comparison is needed. So here's what I'm going to do now. I'm going to actually do some homework. So don't need to read this, that's fine, but here's some homework that I handed out to my class recently. And this homework is talking about motors, rocket motors, and impulse and parachutes, okay? And so for instance, one of the calculations says, what is the specific impulse? ISP, what is the specific impulse for a certain rocket motor? So I'm going to go through that procedure that I just mentioned. I need to find a relationship between specific impulse and other things. So here I pull out the slides, and the slides have an equation. It's right here, and it says the specific impulse, ISP, is equal to the total impulse divided by mg. So I'm going to write down that equation. So, well, here was the question. What is I specific impulse for the motor? Now, I'm not giving you the full context. The homework has brought the students up to this point, and they've been talking about this motor for a while. Okay, and so here is the equation. So ISP is equal to I total, so that's called the total impulse for the motor, divided by MPP, that's the mass of the propellant, the amount of fuel that gets burned in this particular motor, multiplied by G. Sometimes we don't even bother putting the time sign there. We just put mg and we assume that means multiplied by G. So mg, that would be the weight of the propellant. And for this particular motor, I'll pull out a few values here. So now I have a relationship, and it's already solved for the thing that I'm interested in finding. Okay, so that's good. So in this particular case, I total is equal to 236 Newton seconds. That's the answer from a previous question in the same homework assignment. Okay. And the mass of the propellant is equal to 115 grams. And if I would rather that in kilograms, I just need to know what is the relationship between grams and kilograms. And the answer is there are 1,000 grams in 1 kilogram. So cancel the grams, and I get 0.115 kilograms. So that's the mass of the propellant, and then G in the metric system is 9.8 meters per second squared. So let's finish it up. ISP, and I expect ISP to come out in units of seconds. This particular variable has units of time. Okay, so here we go, 236 Newton seconds divided by 0.115 kilograms times 9.8 meters per second squared. Now I'm kind of stuck. And the reason I'm kind of stuck is because I don't see kilograms to cancel this kilograms. I don't see meters to cancel this meters. I see a seconds, but I have seconds squared here, and they're not even going to cancel very effectively. And the reason I'm stuck is because I need to know what newtons are. And in fact, I mentioned it a couple pages ago, and that is 1 Newton, the unit of force, is equal to 1 kilogram times 1 meter per second squared. So what that means is every time I see the letter N, I can replace the letter N with Newton meter per second squared. That's handy because I'm going to use this relationship up here. So let me just say that 1 Newton is equal to 1 kilogram meter per second squared. So now the newtons cancel. And notice the kilograms here cancel the kilograms here. And the meter per second squared cancels the meters per second squared. And all that's left is seconds. Just what I wanted. Okay, so this is an aside. So now I'm back to ISP equals 236 times 1, I guess, divided by 0.115, also divided by 9.8, also divided by 1, and the units are seconds. So, pull out my rusty dusty calculator here. And I have 236 divided by 0.115, and then also divided by 9.8. And I get 209. And the question as posed said, your answer is probably going to be in the vicinity of 170 to 220 seconds. And sure enough, 209. It's right in the middle of the range. So I'm happy with that, and I've circled it to show people that I'm done and that that is my final answer. ISP is equal to 209 seconds for this particular motor. Okay, that was fine. I'm going to continue with the same homework assignment. So if I can find the homework. Another thing that I want to do in this same homework assignment is I want to calculate how fast is the rocket traveling. What is the maximum speed of the rocket at the end of the burn? So when a rocket motor burns, the rocket goes faster and faster and faster. And then when it stops burning, then the rocket goes slower and slower and slower. So the fastest speed is just when the burn is over. And so I'm going to take the information about the motor. I have enough information about the motor now. And basically it tells me that this particular motor burns for a certain number of seconds. I'm just looking for where is that number. 1.15 seconds. Yes, that was from earlier in the homework equation or homework problem set. We got the duration. And then there's a hint and it says use the rocket equation. So again, one of my first steps is to find a relationship. And going back to my slides, here is a relationship. It tells me that the speed of the rocket, if you start at rest, is equal to ISP. We just calculated that number, times G times the natural logarithm. So that's a specific mathematical function. The natural logarithm of a ratio, the ratio of the mass of the rocket before you burn the motor to the mass of the rocket after the motor is finished burning. So that could be a weight ratio or a mass ratio, because the relationship between weight and mass is just a factor of G, and that would occur on the top and the bottom. And then minus G times the burn time right there. So there's the equation that I'm going to be using to answer this particular question. So I'll write down the question just briefly. What is max speed? V1 at end of burn. TB. TB stands for time burn time. Okay. And so coming back to the equation that I found in the slides, I have V1 is equal to ISP multiplied by G multiplied by the natural logarithm of the ratio of the mass or weight before I burn and the mass or weight after I burn. And that's as fast as you could possibly go but I'm going to subtract off what's called the gravitational penalty, which is G times TB. So more or less, if you are traveling vertically, then it turns out that gravity will not let you go as fast as you would really like to go. Similarly, if you're traveling through the air, air friction might not let you get going as fast as you'd like to go. So there might be an air friction penalty, but this calculation only asks us to include the gravitational penalty that associated with going up. So good news. I didn't even have to solve for V1. I found an equation that has V1 ready to go. Let's just pull out some answers, some values to put into this equation. So for instance, we already calculated moments ago that ISP is equal to 209 seconds. I haven't actually decided yet if I'm going to do this in metric or do this in US customary units. This here could be either one. TB, 1.15 seconds. That was from an earlier problem in the same problem set. G could be either 9.8 meters per second squared if I'm doing a metric calculation, or it could be 32.2 feet per second squared if I'm doing a US customary calculation. Fine. Let's do it in US customary. Why not? If we do it US customary, what I would propose that we do is we multiply the mass before we burn times G and the mass after we burn times G, in which case this becomes the weight before we burn. And that was actually given in the problem statement as 40.95 ounces. And then the weight after we have burned is equal to the weight before we burned minus how much we burned, which is the weight of the propellant. And the weight of the propellant is stated in the problem set as 4.06 ounces. Okay, so now I'm essentially doing an execute. In other words, I'm working with numbers here. So let's see, 40.95 minus 4.06, 36.89 ounces. And so I think I'm actually ready to do the calculation. I have a value to go in the numerator and the denominator here. I'm going to take the natural log of that. I have G ready to go. G is equal to 32.2 feet per second squared. I have ISP in seconds. I have time of burn in seconds. And I'm expecting my speed to be in something like feet per second, or if I was doing metric, it might be meters per second. Let's watch for feet per second in this case. Here we go. V1 is equal to 209 seconds times 32.2 feet per second squared times the natural log of 40.95 ounces over 36.89 ounces. That's the weight before I burn the motor. That's the weight after I burn the motor. Minus 32.2 feet per second squared multiplied by 1.15 seconds. Sorry, I'm gonna need to squeeze that in there. Okay, fine. I'm going to do this first on my calculator. So with this particular calculator, if I press this button, it asks me, do I want a basic or a scientific or other possibilities? So here in the scientific version, I actually have natural logarithm available right there. Oh, can't see that with my black pen. Natural logarithm right there, ln. So the first thing I'm going to do is I'm going to say 40.95 divided by 36.89 equals. So there's a number. That number, notice ounces cancels. So this number is 1.11. And then I want to take the natural log of that number. So I just press ln and it says, do you want the natural log? And I say yes, equals. So this entire value is 0.1044. And then I'm going to multiply that by 32.2 and multiply that by 209 equals 702. And what are my units here? This entire thing here is unitless. And here I cancel the seconds with one of the seconds here, and I end up with feet per second. So feet per second. Very good. This is a little bit messy. I'm going to erase this part because this logarithm times that gave me 702 feet per second. Okay. And then I need to subtract off this thing. So 702, I'm even going to write it down, 667 minus 32.2 times 1.15, 37.03 feet per second. That's my gravitational penalty. In other words, I can't quite go as fast as I was hoping to. Okay. So I've got those two written down. Let me just go back to the first one. 702.667 minus 37.03, 665.6 feet per second. And I think the question asks actually, what is that in miles per hour? So it would be handy for me to multiply this, some relationship between feet per second and miles per hour. I'd probably look that up. In fact, let me just see if I have it nearby. Yes. No. I'm going to ask the internet. What is the conversion factor between feet per second and miles per hour? Here we go. MPH to feet per second. So here it says 1.1 mile per hour is 1.47 feet per second. Fair enough. So if that's the case, I just have to take 665.6 feet per second, cancel the feet per second here, and I'll end up with some number of miles per hour, 1.47. Here we go. So I still have that 665.6 divided by 1.47 equals 453 miles per hour. Very good. That's my final answer. And the homework goes on to ask, is that more than the speed of sound or not? And it turns out it's not. Speed of sound is more like 700 miles per hour. That's pretty fast. In 1.15 seconds, I get this rocket up to 450 miles per hour. That's pretty giddy up and go. Okay, last calculation, also from the same homework. And that has to do with parachutes. So the question is going to be, well, here's the question. How fast will your rocket be falling when it hits the ground? Okay, so what is its terminal velocity? So here we go. What is terminal velocity? Vt. If using and let's see, what parachute am I going to be using? How about I assume that I am using a 28-inch diameter parachute? Okay. So I need to find a relationship. The relationship between terminal velocity and the size of a parachute. And here I can find it. It's right here. It says 1/2 times density times terminal velocity squared times the area of the parachute times the drag coefficient of the parachute minus the weight being supported, so this is the post-burnout weight, equals 0. So I'll write that down. 1/2 air density, terminal velocity squared, area of parachute, drag coefficient of the parachute, which is, assume C parachute, CD for parachute equals 1.5. That's part of the problem statement. Minus W1, we know W1 from our last calculation, equals 0. This basically says that forces that act on the object as it's falling produce acceleration, but if it's falling at a constant speed, terminal velocity, it's not accelerating. So the forces will balance and ultimately end up to have the same amount of upwards force due to drag as downwards force due to weight. Fine. I just need a few things here. I need to calculate the area of the parachute. I know this drag coefficient is 1.5. I know the weight because that's from the previous problem. It's 36 ounces or something like that. I'm trying to find the terminal velocity. That's the thing I don't know. And I need the density of air. So I will have to look it up. It's stated in the problem statement in US customary units, but I think I'm going to do this one in metric. Okay. If I'm going to do it in metric, though, I'm going to have to change the diameter of the parachute into a metric value. And if I do it in metric, I'm going to have to change the weight into a metric value as well. So there's kind of pros and cons. One of the best reasons for doing this in metric is the density is much easier in metric. But it turns out that most of my values right now are already in US customary units, so it's kind of going to be a bit of a wash. Let's calculate a few of these things. First of all, let's take this thing and solve it for the terminal velocity. So first of all, I could put W1 on the other side. So I would have 1/2 rho terminal velocity squared times A times C equals W1. And then I can multiply both sides by 2 and divide both sides by rho. And so that would give me VT squared. The A is still over here. The P is still over here. And I have 2 times W1. And I have rho on the bottom. And now I guess I could divide both sides by A and by C. So I get VT squared is equal to 2 W1 over rho, also over AP over CD. And then if I want to solve for VT, I just take the square root of all of that. Twice the weight divided by the air density, divided by the area of the parachute, divided by the coefficient of drag for the parachute. That's my equation. That's sort of my first step, is to get my variable of interest in terms of other things that I could find. Now it's time for me to find all of those other things. And again, let's say a trimetric. So if I'm going to use metric, then I will need values for all of these things here. Some of them I can calculate, some of them from what I know, and some of them I might have to look up. So for instance, it turns out that the density of air in the metric system is equal to 1.204 kilograms per cubic meter. So that's ready to go. The area of the parachute would be pi times r squared, which is pi times, if the diameter is 28, the radius would be 14 inches. And it would be handy if I knew a relationship between inches and meters or inches and centimeters or something like that. I think I actually know one of those. The relationship between inches and centimeters is that 1 inch is 2.54 centimeters. And since inches are squared, I'm going to have to do that twice. And then ultimately, I will in fact want this to be in meters. So I'm going to change centimeters to meters by saying there are 100 centimeters in 1 meter. And since there's centimeters squared here, I'm going to have to do that twice as well, to the power 2. Fine. Let's calculate that out. So pi times 14 squared times 2.54 squared divided by 100 squared. That's the number. And the units, inches will cancel here, inches squared over inches squared, and centimeter squared over centimeter squared. And so ultimately I come up with meters squared. That's great. So I'm going to write scratch, 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 scratch. Let's find out what the number is. So 3.14159 is pi times 14 squared times 2.54 squared divided by 100 squared equals 0.397 meters squared. That makes sense. The reason I say that makes sense is that this is a 28-inch diameter parachute, so about yay big. And frankly, that's less than a meter across. And so definitely it's only going to be a fraction of a square meter, but a pretty big chunk of a square meter. So it's about 40% of 1 square meter. That's the size of my parachute. Okay, that's a good thing to know. I'm also interested in, so I have the density is good to go. The area is good to go. This is just a number. That's just a number. Oh, I need the weight. So let me remind myself from my last calculation that the weight is 36.89 ounces. Okay, so W1 was 36.89 ounces. And I'm interested in changing this weight into newtons. So what I might do first is I might change the ounces into pounds. I know there are 16 ounces in 1 pound. And then I might change the pounds into newtons. And I happen to know that there are 4.45 newtons in 1 pound. So the ounces go away and the pounds go away, and I end up with the weight is 36.89 times 1 times 4.45 divided by 16 divided by 1 newtons. Here we go, 36.89 times 4.45 divided by 16 equals 10.26 newtons. Good. Now I just need to return to this equation. So here we go. Terminal velocity is the square root of 2 times 10.26 newtons divided by 1.204 kilograms per meter cubed times 0.397 meters squared times 1.5. And then remember, newtons are the same thing as kilograms meters per second squared is the same thing as newtons. We've used that before. So let me just look at my units very carefully here. The newtons will cancel. The kilograms will cancel. I have meters squared divided by meters cubed in the denominator. So how about these 2 meters can make 2 of these meters go away. So I have these will cancel with that. And I leave a meters in the denominator of the denominator, which means in fact it's really in the numerator. So this meters goes up and adds to this one. And so ultimately the units are going to be meters squared per seconds squared, because the second squared never got fiddled with. That's good, because the square root of meters squared per second squared is meters per second. That's what I was hoping for. And then here are the numbers. 2 times 10.26 divided by 1.204 times 0.397 times 1.5. Let's calculate those numbers. Here we go, 2 times 10.26 divided by 1.204, and then also divided by 0.397, and also divided by 1.5. 28.62 meters squared per second squared. So if that's the number, here is the square root of that number, 5.35, and the square root of meters squared per second squared is meters per second. There I have it. But I was supposed to compare this to 25 feet per second, which is kind of the safe speed that I'm interested in. So I better change meters per second into feet per second. And I happen to know that 1 meter per second, again, this is just something you can look up or have memorized, is the same thing as 3.28 feet per second. And so the meters per second will cancel, and my answer will be 5.35 times 3.28. And the units will be feet per second. And let's try that. 5.35 times 3.28 equals 17.55 feet per second. Good. So well short of 25 feet per second. So I'm going to call that safe as far as the landing speed. This calculation that we just did is a little bit stranger if you don't do it in metric, because then you have to struggle a bit with the air density, possibly using pound mass. So this is mass per cubic meter, and the air density in US customary units would be something like pound mass per cubic foot. But once you get your grips on that, then you actually have the weight already in US customary units. You have the area in US customary units pretty easily. And so you should, in fact, it's an interesting thing to do this calculation again the other way in the US customary units, and you should again come up with 17.55 feet per second. So a little bit long, but I hope this has been useful just to show that one can do calculations with variables, with constants, with numbers, with values that have units. And it's very useful to keep the units around, watch the units cancel, make sure the units turn out to be the style that you expect. So if you're expecting a time and you come up with a mass, something has gone wrong and you need to fix it. But if you don't write the units, you only write the numbers, you will never notice that something has gone wrong and you might actually report an incorrect value.